Edexcel Decision 1, Graphs and Networks 4, the Travelling Salesperson Problem. Hamiltonian Cycles and the Travelling Salesperson Problem. Okay, so we're looking at this network and we're trying to find possible cycles starting and ending at A. One possible cycle is A, B, C, F, E, D, A. And another possible cycle is A, B, F, C, E, D, A. And what we are asking is, what is the total weight of each of these cycles? So if we look at the first one, A, B, C, F, E, D, A, we've got A to B is 4, B to C is 3, C to F is 4, F to E is 5, E to D is 3, and D to A is 7. Let's see, we add these up, and the total is 26. Okay, so the next cycle, A to B is 4 plus 3, F to C is 4, C to E is 6, E to D is 3, and then D to A is again 7, which is a total of 27. If you notice that both these cycles visit every vertex exactly once, starting and ending at the same vertex, so these are both known as Hamiltonian cycles, as discussed in section 3. So can you find a shorter cycle starting and ending at A that visits each other vertex exactly once? So the shortest we found earlier was 26. So can you find a shorter one? So there is a shorter one, and it is A, B, C, D, E, F, A, and that actually has a total weight of 25. So how would you know if this is the smallest possible cycle in this network? And actually that's a very difficult question to answer, and we're going to look at how we can find an optimal solution to this question in the next few videos. So in the travelling salesperson problem, a salesperson wants to start at one town and visit every town in the network and then return to the starting town, and ideally we'd like to do this by the shortest total route. So note that weights on a graph could relate to the time it takes to get from one town to the next, the distance to get from one town to the next, or the cost. So say, for example, the cost of fuel, or wear and tear on a car, etc. So there's a few definitions we need to know first. We need to remember that a walk is a finite sequence of edges such that the end vertex of one edge is the start vertex of the next. A walk which visits every vertex, returning to its start, is known as a tour. Now a tour is slightly different to a Hamiltonian cycle, because a Hamiltonian cycle starts and ends at the same vertex, but visits every vertex exactly once, whereas a tour can visit vertices as many times as it likes, as long as everyone is visited. So for the classical problem, for the travelling salesperson problem, we're going to think in terms of towns and distances. So in the classical problem, we have a complete graph, and the values on the arcs represent the minimum distances between the two towns. So just a reminder of what a complete graph is. Every vertex in a complete graph is directly linked to every other vertex. So for example, this is the complete graph K4, because it has 4 vertices and everything is linked to everything else. So we want to find the shortest Hamiltonian cycle for this network. And unfortunately there's no known algorithm for finding the shortest of these, other than to find and compare them all, which can be very obviously time consuming. So in a complete network with n vertices, you can show that there are n minus 1 factorial divided by 2 possible Hamiltonian cycles. We touched upon this in section 3, where we looked at K4 and found all the Hamiltonian cycles, only to find that there were 3 unique cycles. And if we look at using this formula, we can see that 4 take away 1 factorial divided by 2 is actually 3. So a network with 6 vertices would have 60 cycles, and one with 10 would have 10 take away 1 factorial divided by 2, which with a calculator is a very large number, 181,440. This is obviously huge, and we wouldn't be able to realistically find all these cycles. So to write down the list is obviously not practical, as we've just seen, but even for a powerful computer it would take a very long time. And here we go. If we look at the computing times for a computer that can find 1,000 tours per second, we would look at the number of vertices, and you can see that even when we get to 12 vertices, it takes a computer 5.5 hours. So if we had 20 vertices, it's unrealistic to ask a computer to do this because it would take 2 million years. So we need to come up with a strategy for the travelling salesperson problem to find an optimal solution. So what we do is we find any tour and we write down its value. Then at least we know we've got one possible solution. So if we were lucky and happened to find the shortest possible tour, then we would have the optimal solution. The only problem is we will have no way of knowing if it is optimal or not. Since we don't know whether it's optimal, we can say that the optimal solution is less than or equal to this value. So this means we will have found an upper bound, and then what we need to do is look for a lower bound to get an idea of how close we might be to the optimal solution. So the rest of the videos will look at how we find upper and lower bounds, and then we'll go about tackling the practical problem. So just to visualize then, what we try to do is find an upper bound that may or may not be optimal. We find a lower bound that does not quite solve the problem. And what we try to do is we try and reduce this interval here by trying to find a smaller upper bound or a larger lower bound. And if we can reduce this interval, then we will be honing in on the optimal solution. If the upper bound and the lower bound that we find are actually the same, then an optimal solution has been found. So in the next section we will be looking at finding an upper bound minimum spanning tree.